Welcome back to the next part of tutorial on heat transfer in the course Basics of Mechanical Engineering 3. I am Dr. Amandeep Singh Oberoi from IIT Kanpur. We have talked about the conduction and we have discussed certain problem statements in that. Conduction is the transfer of heat through medium, that is through the movement of molecules. Now convection is also transfer of heat. This transfer of heat is through fluids, that is through some medium, through gases or through liquids. For example, heat transfer through air, that is convection, that we have discussed. Let me try to recall the concept and take certain problem statements. Convection is the process of heat transfer through movement of fluids, that is liquids or gases. The rate of heat transfer in convection is described by Newton's law of cooling. The law states that the rate at which an object's temperature changes is proportional to the difference between its temperature and the temperature of its surroundings. That is, it simply says the rate of heat transfer Q is equal to H into A into delta T, where A is area of cross section, delta T is the difference between the temperature and the temperature of the surroundings, H is the convective heat transfer coefficient in watts per meter square Kelvin. This you have discussed already. Now certain important numbers are there, like Reynolds number. Reynolds number RE is a dimensionless number that helps predict whether fluid flow will be laminar or turbulent. It represents the ratio of inertial forces to viscous forces within a fluid. If Reynolds number is higher, a specific threshold limit, the flow is turbulent. Within that range, lower than that, it is a streamline flow, or we call it a laminar flow. Then comes Prandtl number. Prandtl number is another dimensionless number that helps to characterize the relative importance of momentum and thermal diffusion in a fluid. Its ratio of momentum diffusivity, that is kinematic viscosity, to thermal diffusivity. Then comes Nusselt number. Nusselt number is again a dimensionless number used to characterize the ratio of convective to conductive heat transfer across fluid, that is Nu is HL by K, where H, as I mentioned, is convective heat transfer coefficient, K is the conductive heat transfer coefficient, L is the length that is under consideration. Let me take a problem statement here. Air at 500 Kelvin is blown over a plate maintained at 303 Kelvin. Case 1, case 2. Case 1, a circular plate with diameter of 10 cm and heat transfer coefficient of 18 watts per meter square Kelvin. Case 2 is a rectangular plate with a length of 6 cm and width of 4 cm and heat transfer coefficient of 35 watts per meter square Kelvin. Compare and determine the suitable plate geometry based upon the heat transfer rate. Now, we have two cases here. Case 1 I will say and case 2. Case 1 they say is a circular plate. It is a circular plate, and case 2 is a rectangular plate. In case 1 they say the diameter is 10 cm, heat transfer coefficient is 18 watts per meter square Kelvin. This diameter is 10 cm and heat transfer coefficient, I would say HC for circular plate, it is 18 watts per meter square Kelvin. And rectangular plate has length of 6 cm and width of 4 cm. Here length is 6 cm and width is 4 cm. Here the coefficient of heat transfer, that is convective coefficient, I will put HR, that is for the rectangular plate, is 35 watts per meter square Kelvin. In the both cases, the temperature that is of the plate is 303 Kelvin. Now, they say air at 500 Kelvin is blown over this plate. Now, we have been given T1 as 500 Kelvin, T2 as 303 Kelvin, and for the circular and the rectangular plates, we have the convective coefficients, which are 18 watts per meter square Kelvin and 35 watts per meter square Kelvin. For the circular, we have the dia as 10 centimeter. For the rectangular, I have length and breadth as 6 centimeter and 4 centimeter respectively. If I convert this into meters, this is 0.1 meter, this is 0.06 meters, this is 0.04 meters. Now, they say compare and determine the suitable plate geometry based upon the heat transfer rate. Now, for a circular plate, let me see what is the heat transfer rate and which one is better. So, for a circular plate, I will say here, and for a rectangular plate, I will calculate on another side. So, here QC is equal to HC into area of the plate into the temperature gradient. So, this area could be expanded. This is pi r square, it is pi RC square into temperature difference, that is T1 minus T2. Putting these values, HC is 18, pi r square would be 0.05 square into the difference of temperatures 500 minus 303. I got the value of QC as 27.836 watt. For a rectangular plate, we have QR is equal to HR into AR into the temperature gradient. Here HR is there, AR is length into breadth, that is length into breadth of rectangular plate times the temperature gradient. Putting the values, this is 35, then I have 0.06 into 0.04 into the difference in temperature, that is 500 minus 303. This gives me the value of QR as 16.548 watt. Now, directly we can see the heat transfer for a circular plate and for a rectangular plate. They say compare and find which cross section would we choose for the maximum heat transfer or better heat transfer. When we see or compare the coefficients here, you can see QC is greater than QR. That is, the circular plate of this dimension that is given transfers more heat than the rectangular plate of the given cross section. This means the circular plate of given cross section is better for maximizing the heat transfer. Here we are talking about the convective heat transfer when the air is blown over the plate. Let me see another problem statement where there is a flat plate. Once again, what it says, there is a flat plate of length 1 meter and width 0.3 meters which is exposed to forced convection. The Reynolds number of flow is RE, that is 2.65 into 10 to the power 5. The Prandtl number is PR, that is 0.682, and thermal conductivity of air is denoted by K, which is 0.0364 watts per meter Kelvin. The surface temperature of plate is 250 degrees centigrade and ambient air temperature is 78 degrees centigrade. Assuming turbulent flow, the Nusselt number of the plate can be determined using this relation, Nu is equal to 0.332 Re per 0.5 and PR per 0.33. Determine the total heat transfer rate from the plate. Now here we need to calculate these numbers, and to calculate these numbers there is a relationship given to calculate the Nusselt number. What we have here is a plate over which air is being blown to. This air is being blown here. This is air at temperature 78 degrees centigrade, and the temperature of the plate is 250 degree centigrade. So because this is at higher temperature, the heat will flow out of this, that is Q is coming out. It is Q through convection. We have the dimensions of the plate, that is it is 0.3 meters. Of width and 1 meter of the length. This is 1 meter. Now we have with us Reynolds number, the Prandtl number, the width is W, that is 0.3 meters. We have RE, we have PR, we have K, that is 0.0364 watt per meter Kelvin, and temperature T1 and T2 are given. T1 is 250 degrees centigrade and T2 is 78 degrees centigrade. We need to find the total heat transfer rate from the plate. To find the total heat transfer, which is Q is equal to H A delta T, we need to find the value of H. To find H is equal to Nu K by L, in this relation here. Here we can say H is equal to Nusselt number into K by L. So we need to find the Nusselt number. To find Nusselt number, the relation given is 0.332 Re per 0.5 and PR per 0.33. Putting the values, this is 0.332. Reynolds numbers value 2.65 into 10 raised to power 5 to the power 0.5, and we have Prandtl number, that is 0.682 to the power 0.33. We get Nusselt number value as 150.45, and this is dimensionless. Now putting this value in the above relation, I get H is equal to 150.45 into K, which is given as 0.0364 watts per meter Kelvin, by the length. Length is taken is 1. So we get the value of H as 5.47 watts per meter square Kelvin. this coefficient of the convective rate of heat transfer is put into this relation, we get the value of Q as 5.47, that is value of H, into area. Area is length into breadth, that is length is 1 and breadth is 0.3. This times the change in the temperature, that is 250 minus 78. This is equal to 282.25 watt. So, value of Q, that is cotton, here is 282.25 watts of heat transfer from the plate. Next, we will take some problem statements on radiation, that is another mode of heat transfer. We discussed about conduction, we discussed about convection, where heat transfer happens due to movement either of molecules or of fluid. In radiation, it is only transfer of thermal energy through electromagnetic waves, most commonly infrared, but it can also be visible and ultraviolet. Unlike conduction, which requires direct contact between materials, a convection which requires a fluid medium, radiation does not need any medium and can occur in a vacuum. For example, heat from the sun travels millions of kilometers through space before warming the earth. The factor that determines the radiation capacity of a body is known as emissivity. Emissivity is the amount of heat that a specific body could transfer in comparison to a black body, which has emissivity value of 1. When we talk about emissivity and its comparison to a black body, it is taken at the same environmental conditions, specifically at same temperature. For example, if at suppose 100 degrees, black body transfers a specific amount of heat. What is the amount of heat this body transfers at 100 degree, which is under test. This we will do a small test under virtual laboratory in the next lectures, when we will discuss about the virtual laboratory demonstration on thermodynamics. Regarding radiation, the net radiative heat transfer between two large surfaces or plates with different temperatures and emissivities is calculated by this formula. When we say large plates, it is large because we need the heat transfer to happen through radiation. It is Q is equal to A into sigma T1 power 4 minus T2 power 4, where T1 and T2 are the absolute temperatures of the surfaces. For example, this is T1 epsilon 1, this is T2 epsilon 2, where epsilon 1 and epsilon 2 are the emissivity of the surface 1 and surface 2 respectively. So, there is radiation that goes from surface 1 to surface 2 depending upon the emissivity of both the surfaces that is there. And here sigma is Stephen Boltzmann constant, whose value is constant, that is 5.67 into 10 raised to the power minus 8 watts per meter square per Kelvin per 4. It is Kelvin per 4 given here. Here the temperature is per 4. So, Kelvin per 4 by Kelvin per 4, this cancels here. Now, let me take a problem statement and we will try to understand how to calculate the emissivity for a specific problem. The problem says, two large plates are maintained at a temperature of 900 Kelvin and 500 Kelvin respectively. Each plate has area of 6 meters square. Compare the heat exchange between the plates for the following cases. Number 1, both plates are black, which means emissivity would be 1. Then both plates have an emissivity value of 0.5. These two problems we will see. So, there are two plates. Which are maintained at the given temperature. It is given temperature T1 as 900 Kelvin and T2 as 500 Kelvin. I will put it here. and here the radiation happens. Radiations from left to right. Depending upon the emissivity of the plates, radiation would happen, and it says it is 6 meters square each. The area in this relation, A is area here. This area from the problem is given as 6 meters square. Now, what we have is T1 as 900 Kelvin, T2 as 500 Kelvin, and area as 6 meters square. Now, case 1. Case 1 is heat exchange. Heat exchange is asked here in the question. What is heat exchange? When we say heat exchange, it is heat transfer. Heat transfer when both plates are black. That means here emissivity is 1, that is epsilon 1 is equal to epsilon 2 is equal to 1. We need to find the value of Q at epsilon is equal to 1. This is equal to A times sigma T1 power 4 minus T2 power 4 over 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Putting the values, area is given as 6 meters square, sigma is Stephen Boltzmann constant, which is 5.67 into 10 raised to power minus 8 into 900 power 4 minus 500 power 4 by 1 over epsilon 1 is 1 plus 1 over epsilon 2 is also 1 minus 1. So, this gives me, I will just simplify the problem because 900 power 4 would be a very big number. This 10 power minus 8 I will take down there. This I will bring it here and here. So, this will turn out to be 6 into 5.67 into 900 by 100 power 4 minus 500 by 100 power 4 by 1. If you see, this is 1 by 100 power 4, which is equal to 10 raised to power minus 8, or this variable was here, this is put here. This value turns out to be 202 kilowatts approximately when epsilon is equal to 1. Second part, they say plates have emissivity of 0.5. For epsilon value is equal to 0.5, we need to find heat exchange, that is heat transfer for given emissivity value, where it says epsilon 1 is equal to epsilon 2 is equal to 0.5. So, therefore, Q here for epsilon as 0.5 is A sigma T1 power 4 minus T2 power 4 by 1 by epsilon 1 plus 1 by epsilon 2 minus 1. Putting the values, area is 6. This also I will simplify like the previous way, 5.67 into 900 by 100 power 4 minus 500 by 100 power 4 by 1 by 0.5 plus 1 by 0.5 minus 1. This value turns out to be 67.3 kilowatts. approximately. This was regarding radiation. With this, my tutorial session on heat transfer is finished. I will try to talk about mass transfer and some applications of the thermodynamics in the coming tutorial. Thank you.